Hi, I am Camilla Baratto. I am a senior researcher in the Sphera group of the National Research Council National Institute of Optics. And today I would like to talk about the effect of light activation on chemical sensor based on aligned nanowires. This work is a collaboration between CNR, University of Brescia, and South Ukrainian National University and the Tampere University. During my talk, I will describe the alignment of zinc oxide nanowires by Langmuir-Blodgett technique to reach a sensor based on individual nanowires for detection of NO2. And I will describe the sensing test in different conditions like heating plus light and light. And also I will describe the growth of intercrossed nanowires, which is another way we selected to realize aligned nanowires. And metal oxide are known since decades to be effective for gas sensing application. In the past, they were used as polycrystalline gas sensor, where the material was deposited as thin or thick film, and the interaction of the gas with the surface of the semiconductors is working with the grain. What is important is the grain size, and to have nanometric grain size is of great importance. The problem could be the coalescence of the grain due to high temperature operation. And this problem can be overcome by using nanowires, where a nanowire is a single crystalline device with a nanometer size diameter. And so you can have high surface to volume ratio along with an increased stability of the material. The best thing to do is to pick up one nanowire out of a mesh of nanowires and to put contacts over it. And in this case, the current variation and the current is flowing through the axis of the nanowire. I select the laser pointer here. So single nanowire sensors are very nice to describe the working of the material, but unfortunately the problem is to make reliable contacts, and one has to use electron beam lithography or focus ion beam to deposit contacts over a selected nanowires. And in literature, it has been proposed to use many nanowires that are similar one to each other, a line between contacts. And different techniques were used to align the nanowires between the contacts, like, for example, the application of an electric field in GI electrophoresis. So several nanowires can be aligned over two cross contacts. Or another approach is to to align the nanowires over a substrate and then to deposit it over each contacts. We in this collaboration we took advantage of the experience of the Tampere group on Langmuir-Blodgett, and we used this technique to align nanowires between two contacts. So basically we selected nanorods, zinc oxide, we kept them with some chemicals to let them float over water surface in the Langmuir-Blodgett flow. And then the barrier were put one near to the other, and this allowed the alignment of the nanowires on the surface, just like trunks in a river. And then we put the chip to collect the nanowires, and the chip has already deposited the contacts. We studied a little bit the geometry of the contacts in order to have conduction only through the nanowires that cross the contacts. The type of alignment depends a lot on the material you select, and we use the commercial nanowires from PlasmaChem. since we have to use a lot of material, 10 milligrams, so other technique to prepare nanowires like vapor, liquid, solid are not good for this technique because they can provide very low amount of nanowires. And the presence of broken nanowires reduce the degree of alignment. Like in this case, you have a worse degree of alignment between the electrodes. So it's important to avoid to have debris. And the current that we can obtain from this type of alignment, where you have just a few nanowires crossing the contacts, just long nanowires are contacting the two electrodes, is in the range of nanoampere, and the curve is symmetric. The current can be increased by shining UV light over the sample. And in the sensing test, our approach was to activate the sensor by means of heating with a hot plate put in the test chamber, and also by shining light, and both. The light used was helium-cadmium laser, both the blue and UV light. And if you shine blue light, you have a small increase by 1 order of magnitude of the current flowing through the sensor in the humid air. Constant humid air was used during the measurement. And in case of UV light, you have an increase of 2 order of magnitude, because super bandgap light can generate electron hole pairs that are available for reaction with what is on the surface. And indeed, an equilibrium condition was reached after oxygen photodissolution during the stabilization period. For sensing, we put NO2 coming from certified bottles inside the test chamber, and we checked the following condition: 200 degrees C plus blue light. Here you have a nice curve, just blue light over the nanowire, and UV light. And from here to here, you have almost a small decrease in the relative response, but a big increase in the response and recovery time. But when you shine UV light, the relative response is comparable to the one obtained in the first case, so obtained here. And response and recovery times are also comparable, because with UV light, electron hole pairs that are made available in the conduction band, that are made available by the UV light shining, are available for participation into the adsorption and desorption reaction of NO2 from the gas, from the semiconductor surface. We tested different NO2 concentration, and from the calibration curve reported here, we can extrapolate the limit of detection, which is 0.2 for NO2 sensing, which is the attention level for NO2 detection outside. H2S detection was not reached at room temperature with UV activation, probably due to the lack of energy to activate the reaction. If we go to the alternative technique we developed during this collaboration, we decide to prepare nanowire by hydrothermal growth using a patterned substrate where the zinc oxide thin film was deposited below the contacts as a substrate, as a seed substrate to generate the nanowire grow. And as you see from this low magnification image, the nanowire grow only at the border of the contacts, and the nanowire crossing the two contacts, if they are long enough, generate conduction. In this case, the conduction is more a grain boundary conduction, like in the polycrystalline sample. And the baseline in this case is much higher than in the case of aligned nanowires aligned by Langmuir-Blodgett, and the effect of UV light is less, because we have only 1 order of magnitude increase. Going to sensing properties, we were able to compare the Langmuir-Blodgett aligned nanowires with the intercross nanowires, and the relative response was nearly the same, but the response and recovery times was higher. Here, the time waited in gas was 1 hour, while here it was half an hour. And so we have a slower dynamic for nanowires. If we consider for this type of sensor UV activated compared to temperature activated sensor, for UV activated we have detection of reducing gases, while no detection of H2S was observed. In this case, at 250 degrees, we have still detection of NO2 with also some detection of H2S. So concluding, we were able to deposit oriented zinc oxide nanowire arrays across electrodes, which can be tested for sensing application. And the condition we selected was working at room temperature with UV activation, which allowed to detect low concentration of NO2. This is also interesting for developing a sensor which works for explosive condition where temperature is not wanted. And also we tested this alternative technique for making intercrossed nanowire device, which also can be exploited for sensing. And I would like to also to acknowledge the funding, which has been used for this research is this NATO project that now ended on developing a multi-sensor system for detection of dangerous and hazardous gases. And I would also like to thank you for watching this presentation, and I am open for questions.